Welcome to Discrete Mathematics, Lecture 9. Today we're going to talk about sets. Okay, so now we've transitioned fully from logic and proofs over into the beginning of set theory. So sets are one of the basic building blocks for the types of objects that we consider in discrete mathematics. So what is a set? It's just an unordered collection of distinct objects which are called elements. Okay, so it's not ordered. We can put them in whatever arrangement we like, and that doesn't change the identity of the set, as we're going to see, so long as they have the same elements. Right, so suppose we have a set A and an object X. This notation X with this E-looking symbol A just denotes that X is an element of set A. And if we have the same symbol, but we have a cross through it, it's just saying that X is not an element of set A. All right, so we've got two ways to describe a set. The first one is going to be called roster notation. Okay, and this is exactly what it sounds like. We're just making a roster. We're just listing out whatever elements are within our set. Okay, so for small sets or for predictable sets, this sort of notation makes a lot of sense, and it can kind of very clearly just show us what's going on in the set. So you might have something of this notation. S is equal to A, comma, B, comma, C. We use these curly brackets to denote a set. Okay, so we can list the elements in any order without changing the set. So the set of S is equal to A, comma, B, comma, C, comma, D is identical to B, C, A, D. Okay, so same elements, different order, same set. Doesn't matter. Okay, the second property here is that listing an element more than once does not change a set either. So we care about distinct elements when we're considering sets. So the set of A, B, C, D is the same thing as A, B, C, B, C, D. Okay, so even though we have these redundant listings of these elements, we've got the same set. Okay, and this sort of thing might just happen if, we've got some sort of complicated definition where the same elements come across from some sort of combination, right? Like if we're talking about real numbers and positive numbers or something like that, right? We might have some sort of overlap or redundancy, but that doesn't change the identity of the set by itself, okay? So our third property, ellipses may be used to describe a set without listing all of the elements as long as that pattern is clear. So we've got an example here where we can see we've got 1, 2, 3. We're just counting our natural numbers upwards. You can throw your ellipses in there and put that final value of 99 in there, right? So this denotes that this set simply contains the natural numbers between 1 and 99. Okay, so this makes a lot of sense when that pattern is very clear, it's very predictable, very easy to convey. Okay, so you could do something similar with even numbers or odd numbers or negatives or something like that. All right. Our fourth property, sets can include unrelated elements. So we don't have to just be talking about letters and numbers or anything like that. We're just grouping together elements. A2, Frederick, the Milky Way, that's still a set. Okay, so that's perfectly fine. It's perfectly valid within this system called roster notation. Let's look at some examples. So we've got the set of all vowels in English. We can denote this as V is equal to, we write our curly brackets, A, E, I, O, U, all separated by commas. Okay, so that's our set of all vowels in English. If we had the set of all positive even integers less than 10, we can denote this with E equals curly brackets 2, comma 4, comma 6, comma 8. Okay. The set of all negative integers greater than negative 100. Okay, so we're going to start with negative 99, and we're going to start listing upwards. We're just going up by 1 each time. So the pattern is clear. We can use our ellipses and throw in our maximum value of negative 1. Okay, so that's where our negative integers end. And I guess this is a quicker way to represent all of these instead of listing out all 99 values. All right, let's talk about some important numerical sets really quickly and see how we can maybe represent them in roster notation. So to start off, we've got the set of all natural numbers represented by capital N, and this is simply those numbers 1, 2, 3, so on and so forth. Now note in this case, we don't actually have a maximum value for our natural numbers, so we're allowed to just throw in those ellipses and just keep going. Okay, the pattern is clear, what we're doing here. Something similar is true for the set of all integers, which is denoted by this capital Z. Okay, we've got 0 in the center, we've got our positive integers 1, 2, 3. We throw our ellipses in here because this side is going to go over to positive infinity. On the left side, we've got -1, -2, -3. We've got ellipses going this way too because this side is just going to go on forever to negative infinity, right? So positive infinity and negative infinity, these are more like directions, right? Sort of like east and west. We just can throw in our ellipses to denote these directions that our numbers are going in. Okay, so those two were fine with roster notation. But then we come across the set of all real numbers. Okay, this is denoted by R. How would we go about actually listing this out with roster notation? Because real numbers aren't just, positive integers, negative integers, 0. They include fractions, right? So now we've got values like a fourth, a fifth, so on and so forth, right? How many of these do we include? We can keep getting smaller and smaller with these. They also include irrational numbers, square root of 2, e, pi, and so on. Okay, so now it's gotten a little bit more difficult. We can't just go by some singular interval from one value to the next anymore, because, how many numbers are between 0 and 1? There's more numbers between 0 and 1 in the real number set than there are natural numbers, because we can just keep breaking this down. We can have this list. We can get an extra 0 in there, right? And we can just keep playing that sort of strategy forever. So this becomes really challenging. And in fact, we actually can't list this because the set of all real numbers is what's called uncountably infinite. We cannot even put a natural number to each of the numbers in the real number set. It just exceeds that far too great. So there's no way to list these out one by one. And if we tried, right, even if we tried and we threw in a couple of our real numbers in there, we would miss uncountably many numbers, right? So -3, -2.5, negative square root of 2, and so on. The change from one value to the next isn't even consistent. It's not clear what the pattern is here. Simply that these numbers are increasing as we go from left to right, but this isn't telling us how we could get the next real number, okay? So this sort of thing is very difficult to establish a pattern, okay? So unlike those simpler cases, we can't make a clear pattern here. And this is going to bring us to our second type of notation for representing sets. And this is going to be a much more definitional sort of approach. Okay, this is called set builder notation. So we write our curly brackets, we're going to put our variable of choice, say x. We have this line here that reads as such that. Okay, so for all x, this is our domain, such that x has property p. So x is meeting some property, some criteria, sort of how we had it with our predicate logic, right? So similar sort of idea. Okay, this is a set of all x such that x has property p. So let's look at some examples. Well, for the reals, we simply can write this is the set of all x such that x is a real number. Okay, and we have separate definitions or ways of defining the real number set as a combination of other number sets and so on and so forth. Okay, so this is a sufficient definition. Okay, this is an established property. We can just refer to it here like this in set builder notation. Okay, we can do the same sort of thing with other sets. It doesn't have to just be these difficult to define sets. It could be something like the set of all x such that x is a positive integer less than 100. Or we've got O here, the set of all x such that x is an odd negative integer less than negative 10. Okay, and these are even things that you could denote by roster notation, but you can also use set builder notation to represent them as well. Then over here, we've got the set is called M, the set of all x, where x is within the real numbers such that x is odd and less than 10. Okay, so with our set builder notation, we can also use predefined sets to specify subsets with more restrictive criteria. Okay, and these are just a topic, subsets, that we're going to return to shortly. But this is another useful quality of set builder notation. We can use these pre-established sets and work within them using that notation we talked about before. And now in blue here, we've got S is equal to the set of all x such that x is, well, in this function, prime of x. So we can also use predicates. Predicates can come back, and we can use these to define sets in a more shorthand way. Okay, so if this is defined elsewhere, you don't even need to write out the entire definition in your set builder notation. In red here, we see some combination, right? So we can use this predefined set, x is within the real numbers. And then on top of that, we can use a definition that is a mathematical expression or mathematical equation. So x is equal to p over q for some positive integers p and q. Okay, and this defines the positive rational number set, which is denoted by q with this little plus sign. And if we had q with the negative sign there, that would be the negative rational numbers. Okay, so set can also be defined using operations, as in this set. All right, so next let's talk about equal sets. So two sets are going to be defined as equal if and only if they have the same elements. So if you remember, if and only if is referring to this biconditional, right? So this is going both ways and saying that, well, Q is necessary for P and P is also necessary for Q. And of course, they're both sufficient for each other. Okay, so this is how they're going to define equivalences or definitions now. Okay, so therefore, if A and B are sets, then A and B are equal if and only if, for all x within our domain, if x is within if x is within set A, then we've got this biconditional, x is also going to be within set B, right? So x being within A implies that x is within B, x being within B implies that x is within set A. And therefore, you can just write this with our equal sign that holds in set theory. A is equal to B. Okay, so let's look at some examples. Are the following sets equal? We've got the set of A, B, C, and D, and the set of A, D, B, C. Well, we've already said that the order does not matter when we're talking about sets, so indeed, these sets possess the same distinct elements. They are equivalent, or they are equal. Okay, well then we've got the set, and we've got some set builder notation here. The set of all x such that x is equal to 2n plus 1, where n is within z. So remember, z is the set of all integers. So n is an integer, x is equal to 2n plus 1. When we were talking about proofs last time, we were using this sort of definition. We used n is equal to 2k plus 1, and this denoted odd integers. Whenever we take an integer, we multiply it by 2. That guarantees it's even. If we add 1, well, we've now guaranteed that it is an odd number. Okay, so this is the set of odd integers. Well, how about this one? This is saying, well, such that for all x, x is equal to 2n minus 1. Okay, this is talking about plus 1, this is talking about minus 1. And again, n is the set of all integers, where n is an integer. So this might look like these are not equivalent operations, but remember, so if 2n is denoting an even integer, what we said last time is that if we shift this either up by 1 or down by 1, we get odd integers in both cases. Now, sure, 2n plus 1 and 2n minus 1 won't be equivalent for some specific n, but when we're talking about an infinitely large set, like the set of all integers, we're going to cover the same values, right? When we're going from negative infinity to positive infinity. So both of these would, for example, have the values 1, 3, 5. They're just going to show up a little bit differently in each list. So this list is just going to be shifted forward by 1. This is going to be shifted backwards by 1. But if we were listing these out, we could start anywhere we like. We could just start the ellipses here. We could have our 1, 3, 5. Same with the second one, 1, 3, 5. Okay, so these are identical sets, actually. Even though their definitions don't look the same, when we're talking about infinite lists like this, it doesn't matter if we shift slightly to the right or slightly to the left, we're covering the same elements, okay? So these are, in fact, equal. All right, then we've got the set of all x within where x is an integer, such that x squared equals 4. And we've got, again, the set of all x where x is an integer, such that x is equal to 2. Well, the second one is really just a single element set. That's just really saying that we've got the set of 2. Because there's only one value that meets this criteria. For the first one, now these might look really similar, but if you remember, we're talking about all integers, not just positive integers as well, right? So there are actually two solutions to x squared equals 4. There's the positive solution and the negative solution. So the first set is going to include negative 2 and positive 2. The second one is only positive 2. So these two are actually not equal. This one has that extra element. If they had put a plus sign here, then these would be equal. Okay, in example D now, we actually do have that little plus sign. So we've got x is a positive integer. And well, then we've got further criteria, x is even, and x is less than 12. And we've got this set, 2n, such that n is a positive integer and less than 6. Okay. So let's see how this looks. If x is even and less than 12, and it's positive, we're going to start with 2. We'll have 2, 4, 6, 8, and 10. Now, let's think about just n for a second. N is positive, so the n is less than 6, so it's spanning 1, 2, 3, 4, and 5. This operation is telling us to take our n's, 1, 2, 3, 4, and 5, and multiply them by 2. So we're going to get 2, 4, 6, 8, and 10. So these are, in fact, identical or equivalent sets. These are just two different ways of saying the same thing. The set of 2, 4, 6, 8, 10. Right? So these are just same things we're saying. So the first one has identical elements. Everything in the first set is in the second, and vice versa. For B, both represent the set of all integers. For C, the first one is negative 2, comma 2. The second one is just 2. And for the last one, both represent this set, 2, 4, 6, 8, and 10. Next, we're going to talk about general sets. So these show up depending on your specific problem, and they're going to take a different meaning in whatever context that you're talking about. So The first one we've got is the universal set, and we represent this with a capital U. This contains everything under consideration. Okay, so all elements that you are currently considering. It could be, however it's defined, it could be all of the numbers between 1 and 100. It could be positive integers less than 12, so on and so forth. So this will change depending on whatever problem or environment you're considering, but that contains everything under consideration. Then we've got what's called the empty set, and this is denoted by this sort of 0 with a slash through it. This contains no elements. The set is quite literally empty, and you can also denote this with just an empty pair of brackets. Okay, so what these do is they sort of establish our minimum and our maximum values, or minimum and maximum sets in whatever environment that we're considering. And finally, we've got what's called a singleton set. This is just a set that contains a single element, for example, the set of just A. Okay, so this is just going to fall somewhere in between these. Now, sets can have other sets as members, just as we were talking about before with subsets and things like that. Okay? So suppose you had the set A. Its members are the empty set, first of all, the set of just this element A, the set of just this element B, and the set containing A and B. All of these sets are members of this larger set, capital A. And I just want to make a note that the empty set is not equivalent to a set containing only the empty set. Okay? So this is a set within a set. This is just a set with no elements. Okay? This outer set does have a single element, the empty set. Okay? So that is just the empty set. This is a set containing one element, the empty set. So there's a distinction made in set theory with this sort of notation. All right, next let's talk about Venn diagrams. So Venn diagrams are just a simple way to visually represent what's happening in a set. Okay. So here we've got this green rectangle, we've got U. This rectangle represents the universal set containing all of the objects under consideration. The circles, now we've just got the one circle here in blue. This is going to represent your actual set. So in this case, we've got the set V. And these little points here are going to represent in red the actual elements of your set. Okay, so we've got the set V of the vowels in the English alphabet, and we've got A, E, I, O, and U as the actual elements. Now in this universal set, you could have a different set for all of the consonants or something like that, right? Here it's not listed, but this would be a separate set that doesn't overlap with our set of vowels and so on, right? And in this case, then the set U would be just all 26 letters of the English alphabet. Okay, so that's Venn diagrams. We'll see in our next lecture video how these kind of come into play and how they can be used to represent different combinations of sets and set operations. All right, next we've got subsets. So we've talked about subsets before. This is a set within another set. The definition is that A is a subset of B because all elements of A belong to B, or if all of the elements of A belong to B. Okay, and it's written with this notation that kind of looks like your less than or equal to sign from mathematics, right? So this is an important part. Okay, so this definition doesn't restrict, actually, that A could be equal to B. They could be equal. All elements of A belong to B, right? That meets this equality criteria as well. But that's not guaranteed by this definition. So it could be that A is just some smaller set within B. It could be that they're equal. So you can kind of think of this sort of as your less than or equal to sign for mathematics. Okay, so A is a subset of B holds if and only if, and we've got this predicate logic sort of definition, such that for all x, if x is within A, x is an element of A, then x is an element of B. It's just saying the same thing as before. Okay, so for every set S, the empty set is in fact a subset of S, right? The elements of the empty set, which are nothing, are contained within every set. It's kind of like saying that there's always like an invisible zero in any sort of expression. That's kind of the equivalent of this empty set being a subset of any set. Okay? And then again, just like we're saying, S is a subset of itself. Any set is going to be a subset of itself because it's going to hold elements that are within itself. Let's look at a couple of examples. The set of all computer science majors at your school is a subset of all of the students at your school. And this first set is indeed going to be a smaller set, presumably. That there's fewer computer science majors than there are students in general at your school. We've got another example here. Well, we've got set A, 1, 2, 3. The set B containing elements 1 and 2. A is not a subset of B because, well, we've got this counterexample. 3 is an A, but not within B. Okay, so A cannot be a subset of B. However, it does go the other way. B is a subset of A because any element you find in B, you will also find in A. Okay, now we talked about equality of sets before. We said two sets are equal, A equals B, if and only if we had this biconditional sort of relationship. Now, if we expanded this according to our definitions of logic, right? So in propositional logic, we said that the biconditional statement between P and Q is the same thing as if P then Q and if Q then P. Okay, you can do the same thing here. You can say that, well, something being in set A implies that it's in set B, and something being in set B implies that it's in set A. But if you look at this definition over here, that implication is the same thing as the definition of subset. So this is really just saying that for all x, if A is a subset of B and B is a subset of A, then two sets are equal. Okay, so two sets are equal if and only if they are subsets of each other. So this is a different definition of equality using subsets. Next, we're going to talk about what are called proper subsets. So a proper subset is, I guess, what we would think intuitively that a subset really is. It's something that is a smaller group within this larger group. It doesn't actually equal the larger group, okay? So we say that if A is a subset of B, but A is not equal to B, then A is a proper subset of B. Okay, they're not equal. This is just a smaller set. And you can see this is denoted with this symbol, and we've dropped that line underneath. So this is much more analogous to the less than symbol for mathematics. So whereas the subset looks like the less than or equal to, proper subset just looks like less than, right? There's no equal to element going on here. A is, in fact, smaller than B. Okay. In other words, if there's an element in A, then it's also in B. That's true for all x with an A. And, or but, there also exists some x that is within B and definitely not in A. Okay. That's why, so this doesn't go the other way as well. Okay, they're not equivalent because B contains something that A does not contain. And you might graphically represent something like this with a Venn diagram. A is just a smaller circle within the set B. Both are within this universal set. All right, next we've got the size of a set. So if there are exactly n distinct elements in S, then we say this set is finite. Okay, so it's some non-negative integer for n. Otherwise, well, it's infinite, just like we've seen before, like the set of all natural numbers and so on. Right? The cardinality of a finite set A is denoted with these sort of absolute value looking symbols, right? This is going to be the number of distinct elements of A. Okay, so we're not going to count redundant elements. So this is the notation for the cardinality of A. And infinite sets have cardinality as well. They just don't have a solid number. They're going to have some sort of infinity. And there are different cardinalities of infinity as well that come up in set theory. All right, so let's see some examples. Determine the cardinality of the following sets. First off, we've got the empty set. Well, the empty set, by definition, is just a pair of empty brackets. They don't have any elements. So its cardinality should be 0. And we've got the cardinality of S, where S is the set of letters of the English alphabet. Well, we've got 26 letters in the English alphabet. That cardinality should just be 26. We're just going to write that number of elements out. That's it. In C, we've got the cardinality of this set, A, B, C, B, C. But remember, it's about the distinct elements. So we don't care about these redundant elements. We want to identify just those distinct elements. The cardinality of this should be 3. And finally, well, we've got the cardinality of Z, the set of all integers. And this is, of course, an infinite set. Okay, so just like we're saying, for that first one, the empty set, this would be 0. Note that, however, the cardinality of the set containing the empty set is 1. That's why these are different things as well, right? They have different cardinality. Cardinality of S is 26, just like we said. Here, again, we're just looking at those distinct elements. That's going to be 3. And of course, the cardinality of the set of all integers, or any of these infinite number sets, would be infinity, right? Or infinite. And like I said before, later on, you can get more detailed and more specific about that level of infinity, countable infinities versus uncountable infinities, right? Next, we've got something called power sets. So the set of all subsets of A, denoted by this notation P of A, is called the power set of A. Okay, so now if we want to list out all of the subsets, you can imagine this might result in a lot of combinations. So our first example, if A is equal to this set where it just contains this little a and little b, then the power set of A is going to be, well, the empty set. That is a subset of A. It's a subset of any set. We've got our singleton sets here, just containing each letter, little a and little b. And then we've got the full set itself, which, again, the full set is a subset of itself, right? That goes back to that sort of less than or equal to idea. So this is equal to the full set. It's still a subset. Okay, so our power set here contains 4 elements, even though our original set only had 2. If B is the set containing just the empty set, well then the power set of B is going to be the empty set. We always start off with that, up to the maximum number of elements contained within the set. So the set containing the empty set. Okay. So even in this case where you have 1 element, you have 2 elements in your power set. And this P of A denotes the power set of A in general. Okay, so the pattern we're seeing here is that if a set has n elements, then the cardinality of the power set is 2 to the n power. Okay, so you can imagine this results in, well, this is going to grow very significantly. We're talking about n equals 2 here for the cardinality of A. The cardinality of the power set is 2 squared, or 4. But what if we had 15 elements, right? We're talking about a power set that contains 2 to the 15 elements. Okay. So that's power sets. Next, we're going to talk about tuples. So tuples are a different structure than sets. These are ordered ordered structures. They're not sets, they're just ordered structures. And you can say something like you've got an n tuple, n being the number of elements within your tuple. So A1, A2, all the way up to AN. And this is ordered. That's the important part here. That's the important distinguishing factor here between tuples and sets. Sets are unordered. Okay, it doesn't matter what order they're in. As long as you contain the same elements, you have the same set. Not the case for tuples. So the tuple 1, 2, 3 is different than 1, 3, 2. Okay? And this is all we're saying. So this is an ordered collection that has A1 as its first element, A2 as its second element, AN on its last element. Okay, so unlike sets, 2n tuples are equal if and only if their corresponding elements are equal. Okay, so for example, this n tuple of A's is only equal to this n tuple of B's if, I should say they're equal if and only if A1 is equal to B1, A2 is equal to B2, so on for every single element until the last two. AN has to be equal to BN. Okay. Now, this might make a little bit more sense in something that we're more familiar with. We've got two tuples, right? So we don't have to always deal with n tuples in some general fashion. You've got two tuples which just have two elements, and these are also known as ordered pairs, just like the ones we would see in our Cartesian coordinate plane. So we've got two elements here in the ordered pair A comma B. We've got another two elements here in the ordered pair, or the ordered tuple C comma D, right? These are only going to be equal. These will be equal if and only if. And we've got this IFF, which is shorthand for if and only if, that you might see later on when you're dealing with more proofs and things like that. So these two are equal if and only if A is equal to C and B is equal to D. Okay, and this makes sense when we were talking about points on your coordinate plane. 1 comma 2 is a different point than 2 comma 1, right? That order has to be the same. Otherwise, they just refer to two different points in your space. Okay, now why are tuples important? Well, they're going to be used in something called the Cartesian product. So Cartesian product of two sets, A and B, and we've got this cross sort of multiplication looking symbol in between, A cross B. It is a set of ordered pairs, or two tuples, little a comma little b, where little a is an element in the set big A, little b is an element of set capital B. Okay, so this is the proper sort of set builder notation definition of the Cartesian product. So A cross B is equal to the set of all tuples A comma B, where little a is in the set A and little b is in the set capital B. Let's see an example of this. And remember, sets don't have to only include numbers, they can include letters or words or something like that. So let's consider just some really two simple sets. Set A contains the elements apple and banana. Set B contains the elements 1, 2, and 3, right? So we're just being really simplistic here. Their Cartesian product involves every combination of elements, okay? From the first set A and the second set B. Now note, A cross B is in this order, so we're going to use the element from set A first, and then the element from set B second. So it's apple comma 1, apple comma 2, apple comma 3, then banana comma 1, banana comma 2, banana comma 3. Okay. So in general, the Cartesian product of sets A1, A2, all the way through AN is a set of ordered n tuples, right? So we had just two sets here, so we had two tuples. If we had n sets, we'd have n tuples, where A sub I belongs to this capital A sub I, for I being anywhere between 1 and n. Okay, so this is just that generalized form of the same definition. Okay. But as long as you understand the two-tuple definition, this is a very simplistic thing to generalize in general, okay? All right, let's look at an example. What is A cross B cross C, where you've got A is a set of 0, 1, B is a set of 1, 2, and C is a set of 0, 1, 2. Well, we're going to need 3 tuples now in this case, right? We've got an A1, or an element A, an element B, and an element C in our tuples, where A is going to run from 0 to 1, B is going to run 1 and 2, C is going to run from 0 to 2. Right? And we're going to put together every combination of those. Okay, and that will look like this. So you take your first element from A, your first element from B, your first element of C, put those together, then iterate through C next. So we've got 0, 1. Now we're going to take the second element of C. Do the same thing. Take the first element from here, first element from here, third element from here. And so now we're done with the combinations of the first 2 elements of these and all 3 elements of C. And we just repeat that process. Okay, now we still take the first element of A, take the second element of B, and then run through C again. 0, 2, 0. First element of A, second element of B, second element of C, and so on, right? All the way until we get to the last elements of each set in this 3-tuple. Okay, so that is the Cartesian product. Now, one more question for consideration. Is the Cartesian product commutative? Okay, so we talked about commutativity before. In this case, is A cross B equal to B cross A? Let's use these sets. A is equal to 1, 2, and B is equal to X, Y to demonstrate. Okay, so remember, we're taking these in the order that they're given. So A cross B is going to result in 1, X, 1, Y, 2, X, and 2, Y. If we did the same thing with B cross A, well, now those X's and Y's have to go first. Okay? So we have the same elements in each pair, but they're in a different order. And if these were sets, that wouldn't matter. The set containing 1 and X is equivalent to the set containing X and 1. But in tuples, that does matter. Okay? Just like the way, like we said before, the point 1, 2 is a different point than 2, 1. Okay, so the Cartesian product is not commutative. Okay, the order does matter here. How about the cardinality, though? Is the cardinality of A cross B equivalent to the cardinality of B cross A? That does work, right? So we do have 4 tuples in each case. So that is going to be commutative. So if, in general, if the cardinality of your set A is M, the cardinality of your set B is N, then A cross B and B cross A both have a cardinality of M times N. Okay, so we're just multiplying the cardinalities of each individual set to get that. That's going to be true. All right, so this was our introduction to sets. If you found this lecture helpful, please give it a like and subscribe so you don't miss the next